Hey guys, welcome to the first session on the measure of science. It's an intro unit to get us into physics, chemistry, anything really where we need to be exact. So our first session deals a lot with scientific notation. As you can see here, we've got measure of science saying that really throughout the duration of the course, we're going to be using the metric system. And so we have common units like seconds, meters, and kilograms. So to start off with, we have to understand that when scientists take measurements, oftentimes, especially when we're dealing with things like space or atoms, we deal with things that are really, really big or really, really small. So for example, I just got a number that's here in kilograms, roughly for the mass of the Earth. And so if you take a look and count out the zeros that are there, you can see that we've got 3, 6, 9, 12, 15, 18, 21, and 24 zeros that are there. So the Earth is really, really heavy, obviously. Uh, the idea kind of behind this is that really every time we want to write this number out, there's a lot of zeros to write out. So we can obviously do this a little bit better, which is kind of the reason for scientific notation. The second spot is going the opposite direction. It's saying that if we had a mass of an electron, it's really small. So you can see how many zeros kind of show up after the decimal in this case. And so if you kind of take a peek, decimal right here, and then we've got that many zeros that are running after the decimal. So obviously these numbers are really long to write down whenever we would need them. So we can use scientific notation and take these long numbers and we can write them in a more compact way. So for instance, we could write the Earth. If you remember in that last slide, I had 24 zeros. So that's the reason why we see our number 6, but then we also see this times 10 to the 24 right there. So our value, our number of zeros are kind of indicated in that spot. And really it's the number of decimal places that we're jumping to get just after the 6, because really that decimal would still be right there. So we could take the mass of an electron, for example. It had actually 31 decimal jumps, but it wasn't just to get to the 9, it was to get to the space just after the 9. First non-zero digit and just get to that space right after it. So we can take a look at a kind of in general rule in what we're looking for. So numbers can be written in scientific notation by using the following expression that you can see here. So we have our m times 10, and then you can see the n that's here and the m that's there. So in general, m is greater than or equal to 1 and it's less than 10. Basically, it is a single digit number that can have decimal values to it. So for example, I could have something like 9.21, or I could just have, like in the last example, and have 6. Numbers that I am not allowed to have for that m value are going to be values that are going to come in, let's change our color here, come in at 0.42. You see that number is less than our 1 that we need to have happen. The other thing is that I can't have scientific notation start off with something like 14.6. That decimal, because its m value is greater than 10, that decimal value actually has to go after the 1 and before the 4. So, for example, we can see that we have a 180 gram softball, which could be written as 1.8 times 10 to the 2. Now, we can look back up and see where our n came into play here. Our n is an integer, which means it can be a negative number, 0, and a positive number. For our purposes, n is not going to be a decimal. It is going to fall in the integer category. So I could have, in this case, 180. The decimal would be after that 0. So really it would kind of fall right there, and then we move the decimal 2 spots over, and that's the reason why you see on our notes here that it's 1.8. Now the times 10 to the 2 is the number of jumps that it makes. It makes 2 jumps, so times 10 to the 2. So let's take a second, if you want to pause, and I'll get you to try out these examples. And when you're ready, just unpause, and we will run through each of these examples to go over the answer. All right, so in the first example, we've got taking a look at the number of jumps to go into there. So that's what, millions and billions, so 25,800,000,000 kilograms. We have to count the number of decimal place jumps that we're making to get to the first non-zero digit. In this case, it's between the 2 and the 5. So as I'm counting this through, I've got my first set of zeros that are there, which is going to be 3 zeros, and then 3 more zeros. There's 6, 7, 8, 9, and 10. So I would have to write this number out as 2.58 times 10, and then 3, 6, 9, 10. Then we put our unit afterward. A popular thing that I've seen in the past sometimes is that people will write 2.58 and then put the unit times 10 to the exponent. Always write out scientific notation first. So all of the scientific notation first, and then your unit comes in afterward. Okay, so our next one, 4,562 millimeters. I have 3 jumps to make to get that between the 4 and the 5, because remember, it has to show up after the first non-zero digit. So I'd have 4.562 times 10 to the 1, 2, 3 millimeters. In our next example, I've got to jump 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 1.496 times 10 to the 3, 6, 9, 10, 11 meters. Now the next one is getting smaller, so the number is less than 1. In this case, I need to start where my decimal is, and I have to get between the 5 and the 4. So I have to count how many decimal jumps I'm moving to get between the 5 and the 4. So I'd have 5.47 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. Now because I'm jumping to the right and my number is less than 1, it's going to be a negative. So negative 9. That tells me that if I wanted to get out of this number, that negative 9 is going to take that decimal and it's going to move it to the left 9 places and should get me back to where I started. Alright, next one over, same thing now. It's a number less than 1, so I'm going to write down my non-zero digits. I've got 8.12, and then times 10, and I'm moving 1, 2, 3, 4 spots over. So because the number is less than 1, it's got to be a negative, so negative 4 seconds. Next one, now I have a number larger than 1 and lots of zeros, so 5.97 times 10 to the 3, 6, 9, 12, 15, 18, 21, 24, and then kilograms. Next one, the decimal is in between here, and sometimes this can get confusing because people don't really know what to do with it. In reality, because the number is quite small, we would probably just leave it at 152. But if we had to round it for whatever reason and scientific notation became a point, for instance, if I needed to round it to the nearest tenth place and we needed that to say that that 0 wasn't a significant number, then I'd need scientific notation. So in this case, I'm going to jump 2 spots to the left, 1.52. I still need my other number because that's 6, 0, 0, 6. Times 10 to the 2 joules. And in the last one, I'm counting how many zeros I have in this big string of numbers, so 1.673 times 10, and then I'm moving 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26 jumps to get just before the 1, and then I need one more jump to get so I'm between the 1 and the 6. So So 27, and it's a negative because the number is less than 1 in kilograms. Okay, so hopefully that went well for you to be able to figure out scientific notation. So in the next section,